Welcome back, Physics 30. This is the CO1.2, work done by a various force section. So CO1.1, we looked at a constant force. So work is equal to simply F multiplied by D, or if that force is at an angle, the horizontal component of that force using cos of theta. Well, now we look at what happens when force is not constant, but it changes as something is being pushed. The best way to cover this is to look at a graphical treatment of it. So yes, a graphical component, it'll help us figure out what will happen in terms of work when the force varies. So if the force acting on an object is constant, as I mentioned, we can simply work equals force multiplied by d. And of course, if that force is directed at an angle, cos of theta will give us that component that we need. In many cases, however, the force varies in magnitude or direction during a process. An example of this includes the force exerted by a spring, which increases with the amount of stretch. So if you stretch a spring, the force increases and increases. Or the work done by varying a force that pulls a box or cart on an even uphill. The work done by varying force can be determined graphically. To do so, we plot our parallel force as a function of d. So as d is getting increased, the force may increase or decrease, etc. The distance can be divided up into smaller segments of delta d for each segment. The average F parallel can be calculated by the dashed line, so we can figure out this. The work done for each segment is W times D, or sorry, F parallel times D. So the average force over here multiplied by D. The force here multiplied by D, etc. And of course, what you see here is what we're really doing here when we take force multiplied by distance. It's really calculating the area of the triangle. Because if you look over here, force multiplied by distance, length times width, it's really the area of a triangle. The total work done to move the object, a total distance of dB minus dA, is the sum of all these little rectangles in here. 5 in the case shown in the figure above. Usually the average value of F parallel for each segment must be estimated, and a reasonable approximation of the work done can be made. If the distance is subdivided into many more segments, delta D can be made smaller and the estimate of the work done will be more accurate. In the limit as D approaches 0, the total area of the many narrow rectangles approaches the area under the curve. So those of you who have taken calculus, you will recognize some of this. So the work done by a variable force, so a force that's changing in an object, in a moving object between 2 points, is equal to the area under the curve. So really what we're doing is we're figuring out the area. For our intent and purpose, we'll simplify the shapes under the curve as rectangles and triangles, just to make it a little bit easier, because calculus is not a prerequisite to this Physics 30 course. So for example, if we had something like this, and if this had been a straight line, well, we can see here it's made up of a rectangle and a triangle. So if we figure out the area of this triangle and the area of this rectangle, we could just simply combine those two together. So if we look at an example dealing with that, determine the work done on each of the following force versus displacement graphs. So if we look at this first one here, quite easily done. So you can see it's a constant force here, right? And if we're moving it 4 meters, really what we're doing is we're figuring out the area underneath there, which is really just the same thing we've been doing. So work is equal to area of, I'll just put area of rectangle shape, which equals length times width, which in our case, 4.0 multiplied by 2.0, so 4.0, 2.0, so that's going to give us 8 joules. And of course, as we can see, really what we're doing with this one is just simply force multiplied by displacement. Force of 2 multiplied by displacement of 4, and we get 8 joules. So that one works perfectly because it is a constant force. But what about a varying force? If we look at the next page, we'll see some of those. So if we look at this example, calculating the work done in this scenario, we can see that the force increases, stays at a constant 3 newtons, then decreases down to 0. And I tried to make it so it's somewhat easy to divide up. I know it doesn't quite match, but I meant for it to match up. So here you have a triangle, rectangle, triangle. So if we're looking for work, we have the area of this triangle. I was going to draw that triangle shape. Plus area of that middle rectangle right here. Plus area of that last triangle on over there. So here we have, I can treat whatever I want as length and width, or force times distance. So with a triangle though, remember half the base times the height, which is really half of a triangle it would make. Plus length times width, plus half the base times the height. So in this case, half of the base here is 2. The height is 3. Then the length times width of this rectangle here, so a length of 3, width of 1. Be careful, just because you see that 3 there doesn't mean it's 3. It's actually 1 in between 2 and 3. So 3 times 1. And a half of this base here, which is from 3 to 4. Of course, that's 1. And the height is 3. So here, a half of 2 is 1. 1 times 3 is 3. 3. And then over here, half of 3. 7.5 joules is the answer there. Okay. Next one. This is an interesting one because we have a negative force, i.e. force operating in the negative direction. So if we're pushing something forwards, the forward force would be in the plus area. If we're exerting a force in the opposite direction, potentially causing an object to slow down, we would have a negative force. So here we go, we have that. And then yes, we can divide this into triangle and rectangle again. So in this case, W is equal to area of that little square on the left plus area of triangle plus area of rectangle. So over here, negative 1 times 1, because yes, we can have a negative. Negative 1 times 1 plus half of the base. So the base here is, let's see, 1, 2 plus, multiplied by 4, the height. And length times width, 4 times 1. Oh, having trouble writing. So let's see, negative 1 times 1 is negative 1. Half of 2 is 1 times 4. That's going to be 4. And 4 times 1 is 4. So we get 4 plus 4 is 8 minus 1, 8 joules. So some of it, of course, is a negative force causing an object to slow down, and the other one is positive. So taking the positive and negative forces into account, we get the work value. When looking at the assignment, question 2 is kind of interesting. A jet takes off from an aircraft via a catapult. The force exerted on the jet is seen below. So it's a varying force. It's a very large force, but then gradually decreases, decreases, decreases. Determine the work done. So we can see here that we have basically a triangle and a rectangle, but since the forces involved here with the catapult are so high, the vertical axis is in terms of kilonewtons. So 1100, not newtons, but kilonewtons. So we'll have to convert that into newtons. So what I did here is I redrew this. So to go from 1 kilonewton to a newton, multiplied by 1,000. So if we multiply 1100 by 1,000, we get 1.1 million. And then 65 here would be 65,000. 85 is still 85 here. So you can just recopy it like this. And of course, so we have this rectangle here, 85 by 65,000. And then the triangle has a base of 85 as well, but of course the height will be 1,100,000, subtract 65,000, which gives 1,035,000 here as the height. So you can do that when figuring out the work. Alrighty, so you should be able to do that and we'll see you again.